Standard electrode potentials. So we talked about the standard potential for an electrochemical cell. And that is going to depend on the specific half reactions that are occurring in the cell. There are two half reactions that make up the entire reaction. One is oxidation, one is reduction. And so E cell depends on which reactions we're using. It's a measure of potential energy difference between the two electrodes. So if we think of each electrode as having its own potential, we can call those the standard electrode potentials. And so E cell is the difference between those two electrode potentials. A good analogy is two tanks of water connected by a common pipe. So here we have a tank of water that has a high level of water and a tank with low level of water. If they are connected through this pipe, what is going to happen to the water? It's going to flow from the higher tank into the lower tank until what happens? Until the levels of the water become the same. And that's because the water in this tank has higher potential energy because it's farther from the ground and gravity's pulling it down. Over here, this tank's water has lower potential energy, and so it's going to move from high potential energy to lower potential energy. The same thing is happening in the electrochemical cell with the electrons. When we connect those two half cells using the wire and the salt bridge, electrons will flow from the electrode with more negative charge. Negative charge is greater potential energy, and it'll flow to the electrode with more positive charge that has less potential energy. There's a lot of positive, negative, greater, less than in this chapter. And I'm sorry, but there's nothing we can do. Electrons flowing from negative to positive should make sense intuitively. Electrons are negatively charged. Are they attracted to negative things or positive things? They're attracted to positive things. So they're going to move away from something that's more negative and towards something that's more positive. They're going from high potential energy to lower potential energy. That's why balls roll down hills instead of rolling up hills, because they're going to a lower potential energy. Any questions yet? Well, we can't measure the electrode potential of a single half cell. There's just no way to measure that directly. So what we do is we just define something as 0 and measure everything relative to that. What is usually used is what's called the standard hydrogen electrode, and will be abbreviated SHE from now on, capital letters, or I suppose you could call her SHE, standard hydrogen electrode. So this is an illustration of the standard hydrogen electrode. It's got an inert electrode in it, platinum, because, good luck getting solid hydrogen, right? It's got an inert platinum electrode to allow the electrons to move around. And this solution is 1 molar hydrochloric acid. So that's 1 molar in hydrogen ions. And this is filled with gas, hydrogen gas, at a pressure of 1 atmosphere. And so those are standard states. The standard state for a gas is 1 atmosphere of pressure. The standard state for an ion in solution is 1 molar. So the reaction that occurs here is 2 hydrogen ions will accept 2 electrons and become 1 hydrogen molecule. And so we all agree, we're going to call that 0. We're going to measure everything relative to that. So that is just because we decided. And sometimes you just have to do that. It's like, okay, this is the reference point. We'll measure everything relative to that. What do we measure elevation relative to? Sea level. Why don't we measure it from the center of the Earth? Because that'd be really tough. There's no tunnel to the center of the Earth. We can't run a tape measure down there, right?
But sea level isn't constant.
Sea level is not absolutely constant, and that is a little bit of a problem, but for most purposes it's good enough. Measurements aren't perfect, right? Yeah. There's error in all of them. So let's look at, this is a zinc 2 plus half cell connected to a standard hydrogen electrode. And so we have reduction occurring in the standard hydrogen electrode. This is the cathode then, and this is the anode. When we draw pictures like this, we always show the anode on the left and the cathode on the right, just out of convention. So over here, the reaction that occurs is oxidation. The zinc metal gives off 2 electrons to become zinc ion. Those 2 electrons travel through the wire, through the voltmeter, and into the hydrogen electrode, where they reduce the hydrogen ions and produce hydrogen gas. So hooking a voltmeter up to this, we get a reading of 0.76 volts. That is measuring the potential difference between these 2 electrodes. Now whether it says plus or minus would depend on what you hook the terminals up to, right? But we're always going to hook it up in the same way. So that only becomes a problem in the lab. It doesn't become a problem in the textbook or problems or exams or anything like that. So we're going to define the standard cell potential as the difference in voltage between the cathode and the anode. And so this is the same definition that we've used with the delta before. It's the final state minus the initial state. So the electrons are going from the anode to the cathode. So E cell is the potential of the final state minus the potential of the initial state. It's the standard electrode potential for the cathode minus the standard electrode potential for the anode. I like it when things are consistent. Final minus initial. We do that all over the place, and so then it becomes much easier to remember. So the voltmeter is showing us that the measured cell potential for that electrochemical cell is positive 0.76 volts. We are trying to figure out what the electrode potential for that zinc half cell is for the anode. We can figure it out because we say that the standard hydrogen electrode is 0. And so 0.76 has something to do with the potential of that zinc electrode. So if we can look at it this way. The potential of the cell is the potential of the cathode minus the potential of the anode. Well, the potential of the cell is 0.76 volts. We measured that with a voltmeter. The potential of the cathode is 0, and so then we can figure out what the potential of the anode is. So the potential of the anode is minus 0.76 volts. And this makes sense because the electrons are flowing from the more negative voltage, minus 0.76, to the more positive voltage, 0. They could both be negative or both be positive, but they'll go from the more negative to the more positive, because a more negative voltage is a higher potential energy. And I think this sentence is helpful. The more negative electrode potential means greater potential energy. Well, that sentence was great until I left out some words. Let me fix. Okay, so I fixed the slide. A more negative electrode potential means greater potential energy of an electron at that electrode. So the electrons are moving away from the anode because of its relative negative charge. The more negatively charged that is, the greater the potential energy that pushes them away. Any questions? If we hook up a copper electrode, a copper half cell, and we look at the voltmeter, we're going to get a standard cell potential of minus 0.34 volts. So this copper electrode has a more positive potential than the standard hydrogen electrode does. Let's just look at the same type of calculation we did. We said that the E cell was One of these minus the other. Which one? Cathode minus the anode. So the measured E cell for this is minus 0.34 volts. The cathode is the standard hydrogen electrode, which is 0. And so then the standard electrode potential for the anode is going to be what? It's going to be plus 0.34, right? And that's what we've got down here. So the anode has a more positive charge than the cathode. Are electrons going to move from this more positive anode to the more negative cathode? No, that is not going to be a spontaneous process. In fact, the opposite will happen. Electrodes will flow from the cathode, which isn't really the cathode then, it'll flow from the hydrogen electrode to the copper electrode. I'm not completely thrilled with how the book is presenting this. Question?
So is the energy supposed to move away from the cathode all the time?
Which you identify as the cathode or the anode depends on what reaction is occurring. So if we set this up for this to be the cathode, then we have reduction occurring at the cathode and oxidation occurring at the anode. And we look at the relative potentials here and we say this is not spontaneous, this is not going to happen by itself. Now, in practice, if you connect those, what will happen is that this reaction will occur at the anode and this reaction will occur at the cathode because the opposite reaction is spontaneous. And I think the way the book is presenting this is a little bit confusing.
How do you determine which is cathode and which is anode?
How do you determine which is the cathode and which is the anode? Let's look at the picture. So when you draw it, you put the anode on the left and the cathode on the right. And this is where the oxidation is occurring, and this is where the reduction is occurring. If it is a spontaneous reaction, electrons will flow in this direction, like we expect. If it's not spontaneous, like if we put copper in here, if we make this a copper electrode with copper ions in here, then the electrons won't flow because the copper half cell is more negative than, is more positive. It's more positive than the standard hydrogen electrode. And so electrons will not leave.
So would you say like the oxidation reaction is always anode and then the reduction reaction is always cathode?
Yes.
Oh.
Yeah. Yeah, and what I don't really like about this example with the copper is what will happen is the electrons will actually go the other way. And so this becomes the cathode, and that other one becomes the anode, and I just think that's really confusing. Isn't that confusing?
So then for the copper, the oxidation and the reduction switch also.
Right, and so what you've got going on over here is you've got oxidation, and over here with the copper, you've got, what am I doing? CO2 plus, you've got reduction. Just because you draw it that way and you call one the cathode and one the anode doesn't mean the electrons won't go the opposite direction. They're going to go from the high to the low. If we look at our water tanks, and let's say we make this one the high and this one the low, which direction is the water going to go? It's going to go the other way, because it's always going to go from high to low. And so what the book is saying is, well, if this is higher and this is lower, then water will not go to the right. Well, that's true. Water will not go to the right, but it will go to the left, right? if there is an open path for the electrons, they will move from higher energy to lower energy. So I think the way they present that is a little bit confusing, right? So you can hook up two half cells, and really, practically, the way you determine the anode and the cathode is you see which direction are the electrons going. The electrons are going from the anode, which is negative, to the cathode, which is positive. And which half cell that is depends on the actual reaction in that half cell. And we're going to learn about that in just a minute. Any other questions? Let's see, did that. So in comparing these two electrochemical cells, the copper electrode, the copper half cell, is positive relative to the standard hydrogen electron. So it's going to draw electrons away from it. It's not going to send them to the standard hydrogen electron. The zinc electrode is negative relative to the standard hydrogen. It's going to send electrons toward, it's going to repel the electrons and send them towards the standard hydrogen electron. And by convention, when we make tables, and we're going to be using a big table of electrode potentials, we always write the reduction half reactions. So they'll show copper 2 plus 2 electrons going to copper solid. Reduction is gain of electrons, oil rig. Oxidation is loss, reduction is gain. So this ion plus 2 electrons, that's a reduction reaction, and then they give the electrode potential for that. This is a standard potential, meaning that this copper 2 plus ion must be 1 molar in the solution for that to be true. Any questions?
What was that last one?
The little circle here means standard, meaning everything's in standard conditions. So standard condition for a gas is 1 atmosphere of pressure. Standard condition for a solid is the pure solid. And standard conditions for an aqueous substance is 1 mole per liter. Now, there are some things that you cannot get at standard state, right, because they're not that soluble. But this is what they would be if they were at standard state. And how they figure that out is something else. So this is half of the table in your textbook showing half reactions. So we've got arrows over here. These are stronger oxidizing agents. If they're stronger oxidizing agents, they are also weaker reducing agents. And they're listed in order of electrode potential. So this is the more positive electrode potential going down, and then as we go down further, they become negative. This is our point of reference, the standard hydrogen electrode in the middle. So we'll be referring to that table quite a bit. So this is kind of a summary of what we've been talking about. The electrode potential of the standard hydrogen electrode is exactly 0 because we decided that. An electrode with a greater tendency toward reduction is going to be positive with respect to the SHE. And so E0 is going to be greater than 0. Greater tendency toward reduction. So that means it's happy about being reduced. Reduction is gain of electrons. And so when we look at this table, things that are positive here are going to be happy about being reduced. These things down here with negative potentials, they don't want to be reduced. They want to be oxidized. So if it has a lesser tendency towards reduction, it's going to have a negative. It's negative relative to the standard hydrogen electrode. It's going to have a negative E0. And the cell potential is the difference between the cathode and the anode. This one at the bottom is probably the most important thing here. Standard cell potential is positive for spontaneous reactions and negative for non-spontaneous reactions. So let's do an example. We're going to calculate the cell potential, standard cell potential, from the standard electrode potentials of the half reactions. So it says use tabulated standard electrode potentials to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees Celsius. The equation is balanced. We can thank the author for that. So here we have a redox reaction. We need to find out what the two half reactions are. So last week we learned about balancing half reactions, right? Yeah. And so this is a real simple one. We can look and write the oxidation states. The oxidation state of Pb2 plus is what? Plus 2. And how about for chromium? 0. Elements have 0 oxidation number. Ions have an oxidation number equal to their charge. So this is 0, and this is plus 3. And that, in a more complicated one, doing that can help you figure out what goes with what. This one's pretty simple. We've just got lead and chromium. So one of these must be 3 Pb2 plus. That's going to have to be, you have to add 6 electrons to that. And that's going to make 3 Pb. And then the other one is 2Cr going to 2Cr3 plus 6 electrons. So this is kind of pulling apart a balanced equation and looking at the two halves. When you pull this apart, you should have the same number of electrons on each side, because when you add those equations together, those cancel out. So now we go to the table in the book, and we find these. Actually, I think I can do this and still make it back. Here's lead 2 plus going to lead solid, and that's minus 0.13. So E0 equals minus 0.13 volts. Let's see if we can find chromium in here. Yeah, I think it's down here. Right there. So chromium 3 plus 3 electrons going to chromium solid. We're not going to find the oxidation reaction that we wrote down. We're going to find the reduction reaction. This is a table of reduction reactions and their potentials. So this one is 0.73. Negative, yes. Okay, and this is where, or maybe we should say another place where I'm going to take issue with your textbook. It's not that they're wrong. I just think it's not the best. So down here, this is what we saw in the table, right? Did I get the number correct? When we did other thermochemistry things and we reversed the direction of an equation, what did we do to delta H or delta G or whatever it was over on the right side? We changed the sign, right? I think that's a more straightforward way to do these problems. So this is the oxidation. This is the reduction. If the reduction has a potential of minus 0.73, the oxidation has a potential of plus 0.73. So that's what I'm going to do. Because I think it's just more consistent and it makes a lot more sense to me.
So if it goes that way on the book, can we decide?
Yeah, if you change the direction from what's shown in the table, then you change the sign. Question?
For finding adding the electrons and the half reactions, do you multiply the charge times the negative?
That's a good question. Since this is multiplied by 3, do we multiply this by 3? No, we don't.
Oh no, I meant like when you're finding the electrons to add.
Oh,
The
okay.
6E.
Find the 6E. Do you multiply
Oh, to find the
two to
6E?
6 plus?
Um,
You can.
Do you multiply times the moles, or is it once you have to get the common?
well, it's a little different when you're taking apart a balanced chemical equation, because this one's already balanced. So I know it's 3 Pb2 plus, and over here it's 3 Pb. To get the 6 electrons, I'm going to put the electrons in here because I need these negative charges to balance these positive charges. So I have a total of 0 charge over here. I need a total of 0 charge on that side. Does that make sense? No, it didn't. That's okay.
What I'm asking is, since it had a charge of 2,
Mm-hmm.
did you multiply by the 3 to get the charge of 6?
Well, this is 3 Pb2 plus ions. So there's a total of plus 6 charge. Yeah. And so we need a total of minus 6 to balance that out.
You won't always be the case. Sometimes, like if you have like the 3 PB minus with a different charge at the other side, even though it's probably not going to happen, you would have a different amount of electrons, right?
In the balanced equation, you always have the same number of electrons on each side. And you can write one that's balanced in mass, but not balanced in charge. So to find the cell potential for this, we just add these up. So that gets us plus 0.60 volts. The coefficients do not affect the electrode potentials. Ooh, so that is different, huh?
Yeah.
Other times, this is 3, or this, comparing this reaction to this one, it's not only reversed, it's also multiplied by 2. But that doesn't matter for electric potentials. Can't handle it, he's walking out. He's disgusted with electrochemistry. I'm going to take that personally. Is this reaction spontaneous?
No.
Yes? No? Hmm?
I'm going to say
Well, let's think. Is this more negative than that?
oh yeah.
Yeah,
It
it
is more
is.
yeah.
So are the electrons going to want to leave here and go to here?
Yes.
Yeah. Something about that doesn't seem quite right.
No.
This is, yeah, that's backwards. Because what is this? Is this oxidation or reduction right here? Reduction is gain of electrons. Gaining electrons, that's reduction, and this is the oxidation. So reduction occurs at the cathode. So here we have our little cell. Those are our electrodes. Here's our anode.
Yeah, your salt ridge.
Yeah, there's a salt bridge. It's a real skinny one. Here's our cathode. So in order for this to be spontaneous, this has to be more negative so that we get electrons going this way. And this needs to be more positive. So reduction occurs at the cathode. So reduction is this one. So it's minus 0.13. We came to the correct result, but it didn't. The reasoning was faulty. The standard potential for this electrode is minus 0.73 volts, because they're always written as reductions. So this one has a potential that's more negative than that one. Okay? So this one's more negative than that one. I find thinking through that to be somewhat painful.
Does that mean
Yes, one has to be oxidation and one has to be reduction.
But on the chart, they're all reductions.
They're all reductions.
Okay.
Because if they did all of them, the chart would be twice as big, and I think it's plenty big already, right? They figure, well, you can flip them. That's not so hard. We don't need to write all of this over again. So this is the thinking behind this. What's easier, though, is to look at the sign of E cell. If it's positive, it's spontaneous. If it's negative, it's not. You have a question? Yes.
I was with you up until the plus 0.6 for E-cell, and then you did some funny business and got lost.
I did some funny business. I was asking, well, let's rewind. Oh, that is really slow. Bless you. Okay, you have a question?
Yeah, the slide where you said the standard E, when it's greater, has a greater tendency, does that refer to the standard E of the cell?
I'll answer that one after this other question, because that's on a different slide. So what I was trying to point out or ask was, is this going to be a spontaneous process? Is it spontaneous, and how can we tell? Well, we can most easily tell by looking at the cell potential. If the cell potential is positive, it is spontaneous. If it's negative, it's not spontaneous. Yes?
So if we were to draw up a little picture to help
Mhm.
us out, don't flip the sign.
Right.
Okay. That
So-
would really throw you off.
Yeah, so, maybe that's why they're going about it that way.
So then if we did it their way, we would leave it as a negative 0.73?
Yeah. So let's do it the book's way. So the book's way says the standard potential for this electrode is minus 0.73. That's what you see in the table. And then the standard cell potential is the cathode minus the anode. You guys ever played Settlers of Catan?
Yeah.
Okay, so look at this. Cat-an. Catan. It spells Catan.
Nice.
I don't know if that would help you or not. Catan, sorry. Cell cat-an. So then you take the cathode potential and subtract the anode potential. Which one's the cathode? Which one's the anode?
-0.13 is the cathode.
What happens at the cathode? Reduction occurs at the cathode. This is the reduction, right? Reduction occurs at the cathode, so this must be the potential for the cathode. Right? Yes. I just had this little brain fart that was not going to work, but it is. And so if this is the cathode, then this is the anode reaction, and we're going to subtract negative 0.73. And what does that get us? Positive 0.60 volts. Same answer, different thinking. So use whichever one makes more sense to you. But the first one makes a heck of a lot more sense to me. For one thing, you don't have to sit down and figure out, okay, was it cathode minus anode or anode minus cathode? Which one's the cathode? Which one's the anode? Oh, I have to watch out for subtracting negative numbers. You just write down your half reaction and the potential from the table. If you reverse the direction, you change the sign, then you add them together. Seems more simple to me. Okay, so Cynthia, what was your question? It was on a previous slide.
Yeah, so the slide where it says, no. Maybe forward.
This one?
Yeah.
Okay.
So, which is that referring to the cell potential?
It's referring to the electrode potential.
Electrode.
The electrode that has a greater tendency towards reduction will be positive. It'll have an E standard that's positive.
So all of the chart stuff is all reduction index.
Right. The chart, all of these are written as reduction reactions.
So like
These are more likely to undergo reduction, and so they have positive electrode potentials. And the ones that have negative electrode potentials, they do not want to be reduced. They want to be oxidized. These are strong reducing agents because a reducing agent reduces something else, right? A movie agent doesn't star in movies. He gets movies for somebody else, the person he's working for. A stronger reducing agent is something that is oxidized and causes something else to be reduced. It's like walking around in a maze, keeping all these things straight. Makes my head hurt. I can't imagine what it does to you guys.
Because it has all those extra electrons, it wants to give them away.
Yeah, they're
Kind of.
kind of, yeah. Okay, let's see where we are here. That's what we just did. So how can we predict if an oxidation reduction is spontaneous? One direction is going to be spontaneous. It's just a matter of which direction is. And so there's two methods. One is to compare E0 for each half reaction. And the more negative electrode potential tends to lose electrons, that's oxidation. The more positive tends to gain electrons, that's reduction. Then look at what combination is going to give you a positive cell potential. So that's one way to do it. Another way is any reduction half reaction will be spontaneous if it's paired with the reverse of a half reaction listed below. Below it in the table. So let's look at that table again. So let's say we had chlorine, reduction of chlorine. Okay, so that has an electrode potential of 1.36. If I pair that with the reverse of any reaction underneath, it will be spontaneous. In the direction I'm writing it, with chlorine being reduced. So chlorine 2 going to chloride, if I pair that with silver metal going to silver ions, this would be negative 0.8 and positive 1.36. That's going to be a positive cell potential. So you can just look at the table, and anything as written with something underneath backwards is spontaneous. Okay? It's a little bit like the activity series for metals. The one on top wins. So the way I think of the activity series for metals, so if you've got, I'm blanking. Let's do zinc and copper. So if you've got copper, that's not copper, that's zinc. If you've got zinc and copper nitrate, we'll make it copper 2 just to be easy. And you're looking at this single replacement reaction. How do you predict if that will happen or not? You look at the activity series. The activity series really comes from these standard electrode potentials, though. So the way I think about this in my fantasy chemistry land is that this is the guy going by himself to the party, and this is the guy, because the metals are guys, and the nonmetals are females. So this is the guy, he's got a date. And they go to this party and they mingle, and the girl thinks that zinc is hotter, and so she leaves with him and copper goes home by himself. I know, right? It's brutal. It's brutal, but that's what it's like out there. At least that's what I'm told. Haven't been out there for a while, but anyway. That's what it was like back in my day. On a list, if this occurs, which I think, I don't know. If this is going to be spontaneous in the forward direction, then zinc has to be above copper in the activity series. And so I say the activity series is like the high school girls' list of cool guys, right? And I would take zinc over copper because he's cooler, right? The same thing is going to happen here. Something up here is going to do what it wants, do it as written, and it's going to make anything else go backwards. So this is the list of who's stronger. You could think of it that way. So fluorine is the strongest. Fluorine can make any of these reactions go backwards. That's kind of cool.
It's weird.
It is weird to think that.
Seems way down there.
So let's see if this would happen, because what are we talking about here? Right? This is zinc 2 plus, so copper 2 plus, and this is zinc 2 plus. So the forward reaction would be zinc going to zinc ions. I mean the first one, which is not reduction, that's oxidation, and copper 2 plus going to copper solid, copper element, that's a reduction. So let's see, here's the reduction. So that's as written, and then I think zinc is down below. Zinc is down here. So copper ion can make zinc go backwards. Does that make any sense? I don't really have much room anywhere to write stuff here, but we've got these two. We've got copper, and we've got zinc going to zinc 2 plus 2 electrons.
Did copper take the electrons?
Yes, copper took the electrons. So this is written as a reduction. Reduction is gain of electrons. Copper is gaining electrons. Copper is stronger, so it can grab these electrons. Zinc is weaker. It's down on the list. Zinc is losing the electrons. Zinc is being oxidized. Okay? So whoever's higher on the list goes forward and makes the other person go backwards. It's kind of like roller skating, I suppose. Somebody has to go backwards. Any questions? I know. So you guys are guinea pigs, right? Because this is the first time I've taught this particular class. So you're getting all the untested analogies, the things that just pop into my head that were completely unrehearsed. And some of them are okay, and some of them are just really bad. And it's all being recorded and published on YouTube.
Sounds dangerous.
It is dangerous. It's exciting. That's,
Oh,
you
never
know.
mind. Okay.
You got it figured out?
Yeah.
Awesome. So here's an example. Nickel 2 and manganese 2. So here's a picture, but let's not look at the picture for a minute. Let's look at this and decide who's going to win.
Nickel.
Nickel is going to win. Nickel has a more positive electrode potential, right? Nickel 2 ion is above manganese on the chart, right? Because it goes from positive down to negative.
Yes.
So what's going to happen with the manganese? It's going to do the opposite, right? It's not a reduction, it's an oxidation. And then I would say that the E0 for that reverse is positive 1.18 volts. And when we add those two together, we get 1.18 minus 0.23. I get a cell potential of plus 0.95.
I have a question.
Yes.
Will we ever get one where it's not at 1 molar?
Yes. That certainly does happen. That does happen. We'll worry about that later. So by looking at these potentials, we can tell which one is going to remain a reduction and which one will be oxidation. And that, when we're drawing the picture, reduction occurs at the cathode, oxidation occurs at the anode, right? So this is the oxidation reaction. That means the manganese half cell is the anode, and the nickel half cell is the cathode. Okay. Without calculating the standard cell potential, predict whether the redox reaction is spontaneous, sketch the electrochemical cell in which the spontaneous reaction would occur. I abbreviated this a little from the book. If it's not spontaneous, we have to figure out how it would be spontaneous and draw the cell that way. And we're supposed to label the anode, that goes on the left, label the cathode, and the direction of electron flow. This could show up as an exam question, right? So here's our reaction. We've got zinc and we've got nickel. So what are the reactions, what are the half reactions here? Yeah, we've got zinc solid going to zinc 2 plus 2 electrons. Is that oxidation or reduction? That's oxidation. He's losing electrons. And the other thing is nickel 2 plus going to nickel. And so that's reduction because it's gaining electrons. Now, how could we figure out, without actually calculating the cell potential, if this is going to be spontaneous in that direction? We have to look at the table, yeah. We don't have to do any calculating, but we do have to look at the table. So we're looking for nickel and zinc. There's nickel, and zinc is below. So nickel gets to go as the reduction. Here, nickel is written as the reduction, and so this is spontaneous. If nickel was below zinc for this, then to make it spontaneous, you just swap the reactants and products, just turn it around. So now we get to draw pictures. So we have 2 half cells. The anode on the left, the cathode on the right. They're in alphabetical order. So there we have our wire. We need a salt bridge. We need some liquid in here. And electrons are always going to go from the anode to the cathode. So that part is always going to be the same. And then we're labeling, we need to label which is which. Which, is this nickel or zinc? It's going to be the zinc. Oxidation occurs at the anode, reduction occurs at the cathode. So this is the zinc half cell, and this is the nickel half cell. Because the spontaneous reduction occurs at the cathode. of red cats, reduction cathode.
So how did you get that it was spontaneous again?
Yeah.
How did I get that it was spontaneous? I looked up zinc and nickel in the table. And I saw that nickel 2 plus, and zinc 2 plus is down here. The table is written as reduction half reactions. Right? So it's nickel 2 plus and zinc 2 plus. Nickel 2 plus is on top, so that one stays the reduction, and this one turns around and becomes the oxidation. And that's what's spontaneous.
So the zinc is written as zinc 2 plus plus 2E, which is opposite of that. So
Right.
That's why we flip it.
Yeah, so this is written opposite of what's in the table. The table is written as a reduction. Here, I know from this equation here that the zinc is undergoing oxidation. So the reduction metal is higher on the list than the oxidation one, and so it's spontaneous. Sometimes I just have to say it several different, slightly different ways, and one of them we just had an aha moment. Anybody else need an aha moment?
Did I get it? Or do
Yeah.
I need it?
Did you get it, or do you need an aha moment?
got it.
You got it? Good. Okay, so at least 2 people understand. That's good. We'll go on. I have to figure out how to get around that. Okay, so we did that. Predicting whether a metal will dissolve in acid. Many metals will dissolve in acid, but not all of them do. It depends on the acid. It also depends on the metal. So when an acid dissolves a metal, it usually does so by this reduction half reaction. It's actually electrochemical in nature. So hydrogen ions are reduced to form hydrogen gas. And we see that, and you stick a piece of zinc metal in hydrochloric acid and it'll bubble and fizz. And magnesium will do that. But you put copper in there and nothing happens. Well, we can use what we just learned looking at that table of electrode potentials to predict whether this is going to happen or not. Is this H plus plus 2E reaction higher than the zinc 2 plus 2 electrons?
Yes.
It is. Because this has a negative E0. And this one is 0, right? Okay, so because this one's higher, it gets to be the reduction, and this one is lower, so it has to flip around and go backwards. And that gives us a spontaneous reaction. Where's copper?
Oh, it's just above it.
Copper is just above this reaction. So when you stick copper, make sure I'm writing here. Copper, copper 2 plus 2 electrons, going to copper solid. This has a higher potential than this half reaction does, and so copper can actually do the opposite. And this reaction is predicted to be spontaneous. Copper metal will not dissolve in hydrochloric acid.
So spontaneous for a metal and an acid means it won't dissolve.
Spontaneous means it will dissolve.
So the first one,
This is spontaneous.
how what's the copper?
Pardon me?
What is the copper?
Copper is not spontaneous. Because, okay, so here we've got, this is a partial list. It's really hard when we don't have the list here. So those lines are just dashes for other things. So there's a very abbreviated electrode potential list. Copper is above hydrogen ion. Hydrogen ion is above zinc ion.
And is the acid always represented by the hydrogen?
Almost always. There's an exception on the next page.
Okay.
So the bottom line is, if you ate a piece of zinc, it gets into your stomach. What's in your stomach? Acid. You're going to be burping hydrogen. I don't recommend that. But it is flammable. I don't think you'd generate enough to actually be able to do much of anything with. So I know you guys are having crazy ideas right now. But if you ate some zinc, it would dissolve in your stomach. If you eat a penny, will it dissolve in your stomach?
No.
No. It'll be nice and shiny clean when it comes out. Don't ask me how I know that. Legos don't dissolve in your stomach either. Just puppies, children. Yeah. You don't take solid zinc. You take zinc ions. There's a difference. Okay. So metals whose reduction half reactions are below H plus on the table dissolve in acids. Those who are above do not dissolve in acids, except. An important exception, nitric acid. Nitric acid, of course, has the potential for this reaction, but it also can oxidize using the nitrate ion. So the nitrate ion undergoes reduction in the presence of acid to nitrogen monoxide gas and water. And this is above the reduction of hydrogen. So nitric acid will dissolve pennies, will dissolve copper. That's the only one your book mentions, so that's the only one we have to care about.
What about dissolving gold?
Well, let's look at the table.
Except for gold.
Where's gold?
Right there.
Gold is way the heck up here. So gold metal would only be oxidized by
Hydrogen
permanganate
Hydrogen peroxide.
and these hydrogen peroxide. But I don't think you're actually going to really get that to go. Just don't use my gold ring to test that out. Yeah, not all the acids are listed here. I think aqua regia.
Yeah, it's a mixture of like sulfuric and
I think nitric. Yeah, yeah. So there are some combinations that can do other things, but yeah. We can be curious about those, but we're not going to lecture about them. Yes?
There was two in 18.5, the nickel and the calcium. Did you mean to do just one?
The nickel, oh, I did just mean to do one, because I thought that was enough drawing.
Okay.
Yeah.
Do they kind of work the same way?
They work the same way, so I thought,